This is content of part 9b. If you are interested only in specific part of this video, just jump to its start time. Once again, I would like to point out that the zero harmonic measurement has many contributions. Basically, all effects which contribute to the second harmonic also contribute to the zero harmonic. Therefore, the zero harmonic measurement should be considered as indirect measurement and should be verified and calibrated by a direct measurement. Next, I would like to discuss how justified the representation of spin dynamics by usage of these two torques. The difference between these two torques is the symmetry, the direction, and the strength dependency on the precession angle. There is another legitimate question: how many types of torque exist? Additionally to these two, maybe there are more torques, which for example might represent the interaction with magnon or photon. Only these two torques may possibly exist for any possible spin dynamics. In order to answer this question, it's necessary to understand the true quantum mechanical origin of spin precession and spin damping. To understand the meaning of a torque within quantum mechanical realm of spin dynamic. The classical description of spin dynamic is based on torques and on well-known Landau-Lifshitz equations. It is very important to understand that Landau-Lifshitz equations only mimics the quantum mechanical process of spin precession. Its purpose to make a simpler classic mechanical description of more complex quantum mechanical mechanism. However, it is important to understand restriction and limitation of Landau-Lifshitz equations. Often, Landau-Lifshitz equations perfectly and correctly describe the spin dynamics, but sometimes the usage of Landau-Lifshitz equation is extended over its limitations, which results in incorrect and confused results. An example of such an incorrect description is use of field-like torque, about which I will explain later in this video. The Landau-Lifshitz equation has two terms. The first term is the precession term, which describes broken time inverse symmetry, and the second term is the precession damping term, which describes transition between spin up and spin down levels. The first precession terms describe the spin precession, which is a natural feature of the broken time inverse symmetry. I would like to remind you the spin itself is just quantity which describes the degree of the broken time inverse symmetry. The precession is natural state of the spin which is not forced by any torque or force. The state of spin precession is the natural or eigenstate of the spin. It is similarly natural for the spin as spin up or spin down states. For example, when the spin up state is a low energy state and spin down state is a high energy state, the state between is a spin precession state. It is as natural as these two states. The wave function of the spin precession state is a linear combination of the wave function of spin up and spin down states. In absence of spin relaxation, the spin would be in the spin precession state forever. Similarly, the spin would stay in a high energy spin down state forever in absence of the spin relaxation. It is important to understand that precession is a very general feature of system of broken time inverse symmetry, and any subject which time inverse symmetry is broken can be in precession state. In fact, it's more clear in system of many spin, all of which are bound in one direction by the exchange interaction. The equilibrium lowest energy state for the system is when all spin is along the external magnetic field H. When a sum of the spin are excited to the upper energy spin down level, but some spins still remain at the lower energy spin up level, there is a spin precession of the total spin. The total spin is quantum mechanical sum of all this up and down spin occupying both the lower and higher energy levels. This fact can be easily calculated. One needs to use spinors and spinor operations for this. After summing up all spin from upper and lower energy level, the spinor of the total spin can be expressed in polar coordinate like this. The angle phi is harmonically oscillating with frequency corresponding to the difference between energy levels, or the frequency of ferromagnetic resonance, or the FMR frequency in short. The angle theta does not change in time and is called the precession angle. The precession angle is directly calculated from percentage of filling spin up and spin down levels here. When the precession angle increases, the filling of high energy spin down level increases, and the filling of low energy spin up level decreases. You can check all detailed maths here or in this PDF file or in this paper. I would like to emphasize once more that this very basic property of the broken time inverse symmetry is calculating using very basic properties of spinors. The precession angle of 90 degrees correspond to equal number of electrons on both levels. Therefore, the first term of Landau-Lifshitz equation just mimics the precession due to the breaking of time inverse symmetry using this vector product, which is also used to describe mechanical precession in classic mechanics. The vector of magnetic field H represents the direction and degree of breaking of the time inverse symmetry. The vector M represents the spin direction of the total spin of localized electrons. It should be pointed out that this vector product describes the quantum precession rather well, as far as the above definition of vectors M and H are strictly followed. The second term of Landau-Lifshitz equation, which is called the damping torque, actually is not a torque at all. It is a classic mechanical mimic of quantum transitions between two quantum levels corresponding to up and down spin directions. When all electrons are on the upper energy level, there is no precession. When some electrons relax to lower energy state and there is an electron on both levels, there is a precession of the total spin. The more electrons transit to the lower energy level, the larger the precession angle becomes. I would like to emphasize once more that there is no torque or force which forces the spin to change precession angle. There is only quantum mechanical transition from upper energy level to the lower energy level. The second terms of Landau-Lifshitz equations mimic this transition in a simple form, which is similar to expression describing a torque in classical mechanics. The expression for the second term, which is double vector product, might look complex, but in fact is very simple. The solution of Landau-Lifshitz equations only having second term without first term is shown here. It is independent of angle phi and describes the direct alignment of the spin along the magnetic field H, as this animation shows. For any initial values of angles phi and theta, the spin aligns along the magnetic field along the shortest path without change of angle phi. It is exactly what is happening in the quantum mechanical case. As more spin-down electrons transit into the lower spin-up level, the precession angle increases proportionally. Once again, I would like to show you this graph of the direct relation between the precession angle and the filling amount of the spin-up and spin-down levels. There is a direct proportionality, similar as described by the second term of Landau-Lifshitz equations. It means that the second term of Landau-Lifshitz equations rather well describes the process of quantum transition between spin levels. At least, it describes well the main tendency. However, there is one problem. If one calculates speed of alignment from this differential equation, it's very different from the rate calculated quantum mechanically. Such calculation you can find in this website, in this PDF file, or in this paper. The problem can be corrected by making this parameter, lambda, which is precession relaxation parameter, dependent on the precession angle. This angle dependence should match the rate calculated quantum mechanically for each specific process, like the spin interaction with a photon or magnon. After doing that, the Landau-Lifshitz equations perfectly describes the quantum mechanical spin dynamics, such as the spin precession and spin precession damping. At this moment, I can answer this important question about how many type of torques exist for the spin dynamics. The answer is there is only one torque, because there is only one possible transition between two energy levels of opposite spin. The expression for classical damper-like torque mimics the quantum transition very well. Different mechanisms of spin relaxation, for example spin magnon or spin photon interaction, should be included in this expression by using corresponding dependence of the lambda parameter on the precession angle. Under some specific conditions, some other parameters of Landau-Lifshitz equations might be affected. It happens when some other parameters of the system depends on the total spin. One such example is magnetization reversal due to the spin injection. In this case, the energy difference between spin energy levels is defined by intrinsic magnetic field as intrinsic, this one, which is proportional to the total spin. Existence of intrinsic magnetic field is feature of ferromagnetic material. When the injected spins occupy the upper energy level, the number of opposite spins increases, the total spin decreases, and therefore the intrinsic magnetic field decreases as well. As a result, the energy difference between two spin levels depends on percentage of occupancy of two spin level. Because of the reduction of energy gap, there are two effects. The first effect is the reduction of precession frequency with increased occupancy of the upper energy level. The second effect is the reduction of precession damping coefficient lambda. The general feature of quantum transition is that the transition probability decreases when the energy gap between levels becomes smaller. For the case of spin injection, it leads to a reduction of the precession damping with increased occupancy of the upper energy level. I would like to mention that the features of quantum transition between two spin levels is slightly different from that of conventional transition between two quantum energy levels, because it requires participation of another particle with a non-zero spin, for example, magnon or photon. It makes the probability of quantum transition between spin levels to be dependent on the spin polarization of the surrounding environment. For example, the probability of the transition from upper energy to low energy level and emitting of shockwave polarized photon is relatively high. However, the probability of opposite transition from low energy to upper energy level and absorption of shockwave polarized photon are relatively small. It is because in a spin and polarized electromagnetic background, there are no shockwave polarized photons. Or to be exact, the number of the left and right shockwave polarized photons are nearly equal. As a general rule, when the environment is not spin polarized, the probability of transition from upper energy level to the lower energy spin level is much higher than probability of opposite transition from lower to upper spin levels. Because of this, the occupancy of upper energy level is much smaller than low energy level, and the occupancy does not follow the Fermi-Dirac distribution. For example, at room temperature, kT equal about 0.026 eV, or which equal 6,300 gigahertz, which is much larger than typical FMR frequency of about 10 gigahertz. It means that in case of occupancy of two spin levels would follow the Fermi level distribution, since this splitting is very small compared to kT, it would be nearly equal number of electrons on each spin levels, and ferromagnetic material would not exist. It is interesting but long story about which I will talk in another video. I just want to mention that there is a similar story for the conduction electrons, for which the energy distribution of the total number of electrons is described by the Fermi-Dirac distribution, but the distribution of spin-polarized electrons is very different from the Fermi-Dirac distribution. You can read more detail about it here or in these papers. I would like to come back to Landau-Lifshitz equations and torques. As I just described, the damp-like torque describes the spin dynamics correctly. Even so, some small adjustments are required to be calculated quantum mechanically. Let's take a look at this recently introduced field-like torque. The question is whether this type of torque describes the spin dynamics correctly. The answer is very definite, no. The expression for this torque is identical to the expression the first term of Landau-Lifshitz equations. Therefore, it describes the second precession of the spin. It means that additionally to main precession along one axis, there is another spin precession around another axis. It's like two precessions occur simultaneously. In the classic mechanics, the existence of two precessions is okay. An object may have two or three or any number of precessions at the same time. However, it's strictly forbidden for quantum mechanics. The spin precession is a feature of the broken time inverse symmetry, and the precession axis is the direction of the broken time inverse symmetry. For a subject, it could be only one axis of broken time inverse symmetry, and therefore only one precession axis. For example, in the case when several magnetic fields are applied to this object, there is only one precession axis, and the precession axis is along of the total magnetic field, which is the vector sum of all applied magnetic field. Assumption that there could be two or more precession axes directly means the assumption that there could be two or more axes of broken time inverse symmetry. It literally means that there are several time axes in our universe. Therefore, such an assumption is a very severe violation of basic laws of our universe. For the conclusion remarks, the spin dynamics is governed by quantum mechanical laws of transition between spin quantum states and features of the broken time inverse symmetry. The mechanical precession of classical object is very different from the spin precession. An equation of classic mechanics which describes mechanical precession can only mimic the quantum mechanical mechanism of spin precession and therefore should be used carefully. The classical form of Landau-Lifshitz equations is the best match for the quantum description of the spin dynamics. The classical Landau-Lifshitz equations with damp-like torque describes well the most features of the spin precession. In contrast, the newly introduced field-like torque does not fit to the quantum mechanical description of spin dynamic. Additionally, the experimental measurements do not indicate any necessity or reason for introduction of such torque. If you are interested to see the content and other parts of this video, you can find the links below this video.